Hey guys, welcome to another video. This video is a part of a series of differentiation videos. So if you want to check out some of them, check my YouTube channel. Otherwise, this specific video is about finding stationary points on a curve using differentiation. Now, I wanted to find a few things first just before we jump straight into it. Now, differentiation, for those who haven't watched other videos and just want to know a bit of context, is to find the gradient of a specific point on a curve. Okay, so if you're given a function that's not linear, so for example a quadratic or a cubic or something like that, and you want to find the gradient, each point on that function is going to have a different gradient. Okay, so what we try to do with differentiation is it allows us to come up with a differential, like a gradient function, and this gradient function is basically a way for us to substitute numbers in to find the gradient of a point, essentially. Okay, so we often differentiate so that we can substitute numbers in to find the gradient at specific points. Okay, now to find a stationary point specifically, a stationary point is a point on a curve or a graph where the gradient is zero. If you're a science person, a lot of people refer to velocity as speed, things like that. And when you throw a ball in the air, for example, if it's like a curve, imagine you do that kind of situation. The velocity, or the, I guess you could say the speed of the ball at the highest point is zero. It like increase in speed, and it'll get to a point where it's like, oh, actually I need to change direction now. It's going to slow down. Like, you can't tell in the eye, but like theoretically it will slow down so much to a very subtle stop, and then it'll go back down, right? So that's basically what we're saying. So we're trying to find stationary points, or points where the gradient is zero. And in this case, we know the gradient is zero if it's what we call a turning point. So of course, exactly what it sounds like. It's basically where it's a point on the graph where it changes direction, right? So you can see if there was the ball here, it went up, up, up. It got to this point and it changed direction. So if we have a cubic, for example, if it looks like that, let's say, our stationary points would be here, okay? So what we're trying to do essentially is, for this cubic function that we're given, we're going to try and find our turning points, right? And at those turning points, it will be a stationary point, and that's when the gradient is zero. Okay, so let's actually answer the question now. So the first thing I want to do, like I mentioned, we're going to try to find the gradient. So to be able to find the gradient at a specific point on a curve, we need to differentiate. So let's differentiate our function first. So dy dx is equal to 1/3 times by 3. I'm just writing it in full here. You can do it in one swoop if you'd like. I'm just going to step it out. 3 take away 1, because you take 1 away from the power, plus 2x to the power of 1, or just 2x. Take 3, and of course, if there's a constant, if you differentiate it, it becomes 0. So we're not putting it on the end. Let's break this down a bit further, make it nice and neat. Those cancel out, because 1/3 times by 3 is 3/1, which equals 1. So that's why I can do that nice and easy. 3 take 1 is 2, so it becomes x squared plus 2x take 3. So this is what we call the gradient function. So now, if we want to find stationary points, like I mentioned earlier, a stationary point has a gradient of 0. So we're going to replace this gradient part of our function with 0, because we want to find out at what x coordinates is the gradient 0. So let's substitute that in. And look at that. Does that look like null factor law to you? So what we're going to do, we're going to factorize. So we're going to factorize the coordinates here. The function here. So two numbers that multiply to give you -3, but add to give you +2. That would be +3 and -1. And of course, null factor law says that that would be -3 or +1. Okay. So that means that these specific x coordinates, so if you had your function, again hypothetical, at the specific point -3 and 1, would you have a stationary point? Okay, that's what that's referring to. That's what these numbers represent. So let's find the y coordinate now of those points. So not substituting it into this is our differential, this is our gradient function. We don't want to put it into the gradient function. We want to put it into the original function. So let's put that into the original. So y equals, our original function is 1/3 negative 3 x cubed plus negative 3 squared, take 3, negative 3 plus 4. Now, once we've put that in, I put that into my calculator, whatever else you want to do, the answer is 13. Therefore, one of your coordinates would be negative 3, 13. I shouldn't have raised it, but again, like I mentioned, you would have had those points. That means it'll hit the y coordinate will be like 13. Remember? So again, if you forget about what we're actually doing, draw the graph and actually link it back to what we're doing, right? So just double check it. Let's do our next one. So our other option was 1. So y equals 1/3 1 cubed plus 1 squared plus 3 times 1 plus 4. And again, I'm substituting that x equals 1 into the original function from the beginning of the question, like at the beginning, right? Put it into your equation, substitute it, calculate it, you would get 7/3. Now, the reason why I'm leaving it as a fraction, and I often do this, I don't often leave it as a decimal, is because it is the most exact answer. When we write something as a decimal, we often have to round, and yes, it's pretty close to the actual answer, but it's not the exact answer. So that's why I often leave it as a fraction. Now, there's nothing wrong with leaving it as a decimal, as long as you write approximately, let's say, for example. Just note that I would probably rather you leave it as a fraction, okay? So that means our second coordinate is 1, 7/3. So again, that means that this is 7/3. Again, you can clearly see this is not to scale because that is not 7/3. That would be a negative number. So just to note, but that's a y coordinate. That means these are my coordinates, and that's our turning point or stationary points. So just to summarize back again, let's start at the beginning. What we did first was to differentiate. The next thing we had to do was to then let dy dx equal 0. Oh, my writing is a bit messy there. Let me just fix that. Not happy with that one. From there, we solve for x. And remember, you can have more than one. And in fact, you probably expect to have more than one answer. And then once you've done that, substitute into the original. So substitute it into the original function, find your y coordinate, and then you would write your answer with the full coordinate. Okay? So I've highlighted them here. Now that should suffice. If it was a worded question with context, you would probably write a worded answer with a worded question. But in this case, as long as you clearly indicate what your turning points are, your stationary points, that's fine. Beautiful. All right. Now, let's actually go back to the question though. Do you see how it says sketch the curve? So we found the stationary points and we know now we've got to sketch it with those points, but we also want to make sure our curve is pretty accurate. Now, we don't know what the graph's going to look like. Like in terms of, just to remember, if you've got a cubic, you can have it that way. You can have it that way, like that. Just note, you probably can't have it this way. I know you've probably seen a few of those before. You can't because you've got two clear turning points here. So in this case, it probably is not going to look like that. So what we need to do is actually figure out, okay, which one is it? Is it this one or this one? Is it like the flipped version or not? So let's look into it. Now we're going to use something called the sign test. Now I'm going to bring those coordinates back up. So they were -3, 13 and 1, 7/3. Okay. So what we're going to do is test to see the nature. So if you see the word nature, it often means if it's a maximum or minimum. As a refresher, this is our minimum, happy face, and a maximum, this is sad face, if you remember it like that. So you've got two different ways because you need to figure out, because obviously when you sketch it, let's say like that, that's going to be a minimum and that's a maximum. But we don't know just given points. We actually need to test it. Now, the way we're going to test it is using called the sign test. Now, the way the sign test works is that you test the x coordinate by zoomed in here. It's not very good. So if I really tested this, if this was a minimum, if that was negative 313 here, if it was a minimum, then your one's either side of it, your y coordinate would either be increasing or decreasing, right? You would see that it would, the gradient would either go like that or like that. You know, it could also go the other way if you had 313 here. The x coordinate before that, when x equals 2, it could be a positive, then a negative. So what we're going to do, we're going to use the differential function, the gradient function, to see what the gradient is on either side. And it's going to help us figure out whether or not it's a max or a min. Okay, so let's break this down. Let's get rid of all my artistic scribbles. As lovely as they are, they can go. So let's try it. So we're going to just look at this point. Okay, so if I've got my x coordinate being negative 3, let's test either side. So a bigger number would be negative 2. A smaller number would be negative 4. We're going to substitute it into our differential function, our gradient function, and we're going to figure out if the answer is positive or negative, because that will tell us if the gradient, again, is positive or negative. So if I substituted in, this is what I would write in my calculator, by the way. I'd literally write, you would write negative 3 squared plus 2. Well, I don't need brackets for those actually. 2 negative 3, take 3, and you would see if your answer is positive or negative. So I'm just getting that from this, by the way. I'll put in green. That's where that's coming from, by the way. I've put negative 3 into that function. So I'm going to put that to my calculator. Your answer will be 5. Okay, so if you went through and actually did it, the answer is 5. 5 is a positive number, so it's going to be a positive gradient. So because it's positive, it's going to go like that. Now, remember, this is a stationary point. At a stationary point, the gradient is 0. That means it's kind of like the curvy part, right? The gradient 0 is flat. So let's try negative 2. So I'm going to go through now, do the same thing, and instead of putting negative 3 in there, I'm going to put negative 2, right? So if you put that into your calculator, you'll get negative 3, which is a negative number. Negative number has a negative gradient. It means it would go down like this. And do you see it kind of makes like a curve shape? So that indicates to you that this coordinate, the negative 313, is going to become a maximum, okay? Now, you can also test it with this one here. You can do the same table situation and you can try and figure it out. But I could probably tell you without calculating it's going to be a minimum. How do I know that though? Like, why can't it be a maximum as well? So the reason why it can't is because since you're told that negative 313, at that point you know it's going to be a maximum at, what was the coordinate? 177/3. Let's say that's there, 7/3, not to scale. If that was a maximum as well, right, it would mean that you would have to require some sort of change in direction again, which would indicate another stationary point. But we don't have another stationary point, so that can't be possible, right? Because there's no way you can have a maximum turning point here if you already have a maximum here. So just because of the nature of a function that's a cubic, it would indicate that you would have to go like that. Okay, it would have to be a minimum shape for it to be cubic. Okay, just through pure nature of it. Okay, so without actually testing it, let's go through that again. So let's recap. So I've got negative 313. That is a max turning point. And as we discussed, negative 1/7/3 is a minimum turning point. There is just one little bit of information I also would like to include, which is the y-intercept, to show that this intercept is makes this sketch more accurate, right? So what I'm going to do, I'm going to put in find my intercept. Now, the way you find the intercept, thankfully we were given the rule in general form. So when it's in general form, the constant at the end with no variable, so in this case 4, indicates to us that it's a intercept. So this 4 is a y-intercept. So now I've got an additional piece of information here without actually trying. 0, 4 is my y-intercept. Now, I am not going to go deep into finding the x-intercepts, the roots, just for this video. You absolutely could. Because it only wants you to sketch stationary points, that's why I'm going to stop here. However, if it literally just actually sketched the function and didn't specify like specifically stationary points or anything, I would go through, find all these things as well as the roots, which is a different story. But for now, I'm just going to show you how to sketch the graph using the stationary points and the y-intercept. So let's do it, shall we? So I'm going to just cheat here a little bit and actually sketch our little axes here. I'm going to make it red. I'm also going to make my pen a bit thicker. Okay, so we talked about how -3 and 1 had our turning points. One of the turning points was at 7/3, which is about 2.3. So it's about, I'm going to say here. And then I'm going to say, like, say 13 is up here. Again, not to scale. Okay. So here's one of our turning points. Here's the other one. And we talked about how that's a maximum and that's a minimum. We also need to include our intercepts. So let's say our intercepts 4 here. It has to go through this point as well. Okay? Because of the nature of the graph, it has to be in this kind of format. Okay? Goes through our turning point, has to go through 4, and then come back up again. Okay? Now, again, I haven't specified what that is. It doesn't matter. But because it's asking us to graph specifically some points, let's put it in. So we're going to specify our coordinate is 0, 4. That turning point is 1, 7/3. That point is also -3, 13. Okay, and we clearly are showing the nature as well. It's clearly a maximum and clearly a minimum for those 2 points. All right, so that's what the graph would look like. Thanks very much for watching. Bye.